Thank you, everyone, for joining us tonight. I'm going to give you a few rules. We're going to have a talk for about an hour. And if you have questions, I'm going to ask you to type them in the chat space on the Vimeo feed, and I will try to orchestrate a few questions at the end of the talk. So for those of you who do not know me, I'm Ed Mitchell. I'm the director of the School of Architecture and Interior Design at DAAP. And tonight it's my great pleasure to introduce the 2020 Chatterjee lecturer, Patrick Bellew, founding director of the engineering firm Atelier 10 in London, where he will be broadcasting from, or just 45 miles outside of London, as the case would be. But first, let me say a little bit about the series that this lecture is part of. Tonight's lecture is supported by and named for Janet and Jay Chatterjee and other generous supporters. Jay Chatterjee is the Dean Emeritus and Professor Emeritus of Architecture and Planning at the University of Cincinnati. Dean Chatterjee joined the faculty here in 1967 and later as the Dean from 1982 to 2001. He reorganized DAAP from a departmental to a school structure. During this time as administrator, he led the physical transformation of the campus from a commuter school to an internationally renowned campus that features signature buildings by a world-class roster of architects and landscape architects. As a citizen of Cincinnati, Dean Chatterjee participated and led numerous civic and professional organizations, always doing his best for the city as well as the university. And I've had the great good fortune of working with Dean Chatterjee on several projects. He did some lectures for our school last year, and he's wrote me into doing a book with him. And I can personally attest to his great generosity and wise mentorship. And I'm delighted that he can pass on his commitment to education to yet another group of DAAP students through this lecture series. So each year, one of the 4 school directors of the college helps to choose the speaker. Jay's commitment to architecture, landscape, and public stewardship motivated his specific request to me. Last January or February, I think it was, he told me he wanted to find a speaker who was an innovative environmental thinker. Now, we all know the worldwide concern about the widespread impact of global warming that we witness daily and see in the news every day made this both timely and urgent. And this underscored our schools and other schools and the college's concern to be diligent and mindful of our roles as designers and looking at the impact on the planet. At SAID, the School of Architecture and Interior Design, we're already working on building a strong foundation to gain expertise in this area. Patrick Bellew, a real pioneer in numerous innovations in the built environment, immediately came to mind as the speaker. And so we called him right there and then and convinced him to do this talk. And we were hoping very much that he would be here in Cincinnati today. And I know he looked forward to that as well, but we're very lucky to have him here remotely tonight. Like Dean Chatterjee, Patrick Bellew expands upon sometimes narrow definitions of what environment might be to consider that term not as a static definition of calculable values, but as a series of questions that need to be asked. Namely, what is the environment of the building, the site, the city, and what is the disciplinary ecology of design practice? How do we need to expand the fields we work in to think more broadly about the context in which we work? And when we talked about a date in the fall, it was just a happy coincidence that it also marked the 30th anniversary of the founding of Atelier 10. So Patrick thought that was a timely time to do this talk in October, made a lot of sense. Atelier 10 is a firm which he founded and has been a leader in creative engineering. Patrick's worked with architects that include Diller Scofidio Renfro, Zaha Hadid, Sir Norman Foster and Partners, Frank Gehry, Sir Michael Hopkins, Grimshaw, OMA, Sana, and many, many others, too numerous to list today. The firm has grown from its original central base in London and now includes 11 offices worldwide, all focused on the delivery of high-performance buildings. Patrick has many awards, which would again take our entire hour to list all the RIBA and AIA awards and other international honors that the firm has achieved. But some of those include Patrick being named one of the UK's royal designers and a chartered building services engineer. In 2006, he founded the UK Green Building Council, served as a member of its executive board from 2006 to 2010, and he now sits on the trustee board. He's taught as a frequent visitor at the Yale University School of Architecture since 2000, where he has held the Eero Saarinen Visiting Professor from 2010 to 2017. I believe we'll renew that again probably in the next year or two. He was on the design review committee of the Commission for Architecture and the Built Environment in London from 1999 to 2003. He was a governor of the Building Centre Trust in London between 1996 and 2011, and sits on the employer panel of the Construction Industry Council. Patrick's success in integrating innovative technologies with noteworthy architecture has been acknowledged by the Royal Institute of British Architects, who made him an honorary fellow in 2001. He was elected a fellow of the Royal Academy of Engineering in 2004 and delivered the 6th Happold Medal Lecture and received the Happold Medal from the Construction Industry Council and the Happold Foundation in 2008. In 2010, Patrick was named a Royal Designer for Industry by the UK's Faculty of Royal Designers. And in 2013, he was the recipient of the Chartered Institution of Building Service Engineers President's Silver Medal. On a personal note, I met Patrick 20 years ago, I guess it was, and he's taught me new ways of thinking and drinking, and he's given me lessons that he learned from past technologies about the natural environment and elaborated on how they might be incorporated into thinking about how buildings perform. And equally important, he and his collaborators also greatly appreciate the value that good design can create, how good design can create meaningful, sustainable, and yes, beautiful and lasting spaces. Like tonight's lecture sponsor, Jay Chatterjee, Patrick shares a warm generosity of intelligence and good spirit that causes architects and institutions to seek him out for either a friendly chat or real professional advice on how to make a positive impact on our environment. So on behalf of the college and the University of Cincinnati community, it's a personal honor and a real pleasure and our great good fortune to welcome Patrick Bellew as our 2020 Chatterjee Lecturer. Patrick?
Oh, Ed, thank you so much. I'm embarrassed by the eulogy. I hope I can live up to it. Hey, everybody, good evening. It's a thrill to be here talking to you. Well, it's not a thrill to be here because I'm in my barn in Old Hampshire in England, where we're kind of locked down again, and but in good health, and I hope you are all too. I'm going to try and fill the next hour or so with just some thoughts and reflections and some projects and some observations on how the world is at the moment. Ed has already done a bit of the commercial for me. As I set the company up 30 years ago and have been involved in its work of trying to bridge the gap between architecture and engineering for all of that time. I set up Atelier 10 in collaboration with a very close friend and also a teacher at Yale, a guy called Neil Thomas, who, if you haven't heard of him, should look him up. Neil Thomas of Atelier 1, who's currently doing amazing work in the world of both of rock and roll and fine art and bamboo. And if you're interested in bamboo as a building material, look up some of his talks, incredible. But Neil and I started the Atelier group together, and our first meeting was through association with Happold, with Ted Happold, who's the guy on the top of those three pictures. I was fortunate enough to study under Ted. I only went to Bath University to study environmental design because I went to a talk by Ted talking about the Centre Pompidou and the Sydney Opera House that he was working on at the time. And he basically started a course at Bath that it said that we have to work more closely together. So architecture, structural engineering, and environmental engineering were all put in the same room for 4 years and left to simmer gently. And we all got degrees that joined together, 2 years of architecture followed by 2 years of engineering, and the architects got 2 years of engineering and architecture followed by 2 years of architecture, or 5 years of architecture. So from the very beginning, I was sitting with structural engineers, and I was fortunate enough to work early on with Ian Liddell, who's the guy on the left, who's one of the UK's leading lightweight structure specialists, and then Fry Otto, who all of whom gave me an object lesson in what structural engineers do, which was always to try and minimize the use and the demand on the materials by using all kinds of low cunning in the way of understanding tension and compression and those sorts of things. And as far as I could make out, I'd chosen a stream about, to be a building services engineer. The only thing the building services engineer did was to calculate what the worst thing that could happen, then add 20% for safety, which of course a structural engineer does, but they can be more reductive. And then size all the kit to be very inefficient for its whole life. And there didn't seem to be a connection between architecture and engineering. And so I set out my sort of journey, if you like, began in trying to explore that distance, to try and bridge the gap between architecture and engineering, because it seemed to me there was an obvious one. And I'll come back to that in a minute. So as I said, we've now sort of have a bit of a global reach. We're working on projects near and far, from Google's headquarters in London to Yandex's headquarters in Moscow, to a beautiful building with Zaha's office in the Gulf. But we also work down in Australia with a UN studio project, South Bank by Bellew in Melbourne. And we've done pavilions for many years. We've done the British pavilions. For some reason, we seem to keep winning them. The one with Thomas Heatherwick. And we're currently in construction at the moment for what's going to be Dubai 2021, the British pavilion with the wonderful Ez Devlin. We set up in America 20 years ago. That's when I first came to teach at Yale. And since then, we've been blessed with some incredible projects to work on, including recently completed actually a few years ago, SF MoMA. We're currently working on President Obama's library in Chicago, and many other buildings besides. So we've had a really great journey. But that journey is always at the center of all our conversations, is a basic concern for the things that we do having as little environmental impact as they could possibly have. And when I do these talks, I always slightly hesitate to beat you up with conversations or thoughts about how bad things are. But it is important that we recognize what's gone on. But it's also important maybe for the generations to recognize that it's not exactly news. It's interesting when you read back into even into the early 60s, people like Bucky Fuller were already saying, he was, I think, of anybody sort of in that period, almost coined the title sustainability, because he talked, although he was a structural engineer, he talked about Spaceship Earth, the damage we were doing to it, and the importance of being sort of minimalist. And I didn't start to understand Bucky Fuller probably until the 80s. I said nobody really understands Bucky Fuller, but you know what I mean. You just start to get to sort of read into what he was saying. But he was the guy who started to talk about a blueprint for survival, even in the 60s, and he got pretty roundly ignored by most people. In the 70s, Barbara Ward and the Club of Rome, Only One Earth, and they talked about reaching the limits of the planet to support us. It wasn't really about poisoning the planet. It was more about exhausting the resources on the planet and setting limits to growth. And actually, that passed our profession by almost unnoticed. But also what happened, of course, is we didn't run out because we became better at finding things, and the resources have lasted longer. In my lifetime, the price of the oil used to drive everything in our middle years, from the 60s to the 2000s. And we certainly, people started to become more aware of the need for conservation just because of the cost of fuel. So that became a driver until the fuel price dropped again. The first real big environmental thing that moved the dial was the hole in the ozone layer in 1987. And they were talking about, it happened up to 1987. And the imminent catastrophe as a driver for change. The Montreal Protocol, which basically banned global warming of materials that had high global warming potential, and particularly refrigerants, was one of the first really effective global movements to change. And in fact, the hole in the ozone layer was reversed, and things are a lot better. I'd say that CO2 emissions are beginning to have a similar impact to that. Then, of course, your very own Al Gore in 2006 started to spell out the crisis of global warming. And he certainly moved the dial a little bit. At the same time, industrialists and economists were starting to read about actually how business that followed the green. I think Esty and Winston in this book from some two teachers at Yale talked about green wave riders, and they demonstrated how companies that had followed the green agenda actually were outperforming those that didn't. And that started to make people realize that that being sustainable and being more efficient wasn't necessarily about spending more money and being worse off. You actually, if you weren't doing it, you were not going to be as well off in the long term. So they were proposing a kind of green movement as not only a sustainable thing, but a sustaining thing for business in the future. So now we move to more recent times in 2016, the Paris Accord, where most countries have signed up to significant carbon reductions. And that is the thing that's most significantly affecting legal and our codes of practice around the world, are most affected really by the sign up to the Paris Accord. At the same time, we've got this sort of parallel path, which is of doom and gloom. There's a book called, if you want a great read, David Wells's Uninhabitable Earth is a terrifying story. It's quite hard to get through, but it really talks about the dangers that lie ahead if we don't do something. And of course, the global CO2 levels continue to rise despite our efforts to try and reduce them. So in the last couple of years, what's happened in the UK, I don't know if David Attenborough gets across to the US, but there's been a massive change in the way we think about plastics and waste through a program started in England really by this film called The Blue Planet, where there was this terrible footage of turtles wrapped in plastic and microbead plastics and so on, which was totally shocking. Greta, of course, and her I Want You to Panic starting to inspire the youth against it. And then also cities starting to act. San Francisco, New York passing really ambitious climate targets. And in the UK, yeah, not so much, but we're starting to get there and starting to get much more ambitious climate targets. I shouldn't put that picture up of poor Theresa as she was leaving office, but she didn't do very much. But the mayor of London has been pushing things, and that's spread out across the UK at a mayoral level. So that's we're definitely starting to see that. And right now, of course, we're all a bit obsessed with COVID, and it does show that if the world sets its mind to doing something, and I don't mean the disease itself, I mean reacting to the disease, we can make things happen. Bill Gates said COVID-19 is awful, but climate change will be worse. And I think the idea that we carry on ignoring carbon and climate change as an issue is no longer a realistic place to sit. So it's very much what our whole industry is focused upon. So I'm going to wind the clock now back a bit to kind of talk a little bit about sort of the history of architecture and vernacular architecture and the environment. And in the time before we had building systems, both animals and people, animals haven't got building systems, but people have found ways of living, of building architecture, making architecture that would help them to survive in tough conditions. There's lots of stories around this, and I'm sure most of you would have read stories about how vernacular architecture responds to climate, but whether it's through wind towers, through thermal mass, or through simple use of sort of multi-layer insulation in an igloo, you can make survivable structures out of very simple materials. And in architecture pre-air conditioning, even some iconic 20th century buildings, you see things that you don't see on buildings now quite so much. So the Flatiron building from 1902 predates in New York. It predates the air conditioning. It's in Madison Square. And what you see on this lovely photograph from that period of all of these buildings around the space is external shades. Because they couldn't cool, they kept the sun off the windows and they kept more comfortable, and the shades were just an angle to allow the windows to be opened, and the plan was narrow enough to let the building naturally ventilate. Now, all those shades have been replaced with window shaking air conditioning units, and that's in the name of progress. And it shows, in a way, we almost never put shades on the outside of buildings in the UK or in America. They do a lot in Europe, and it's something that you just don't see. The Chrysler building is planned around natural ventilation, believe it or not. And the simplicity of these forms is the forms are based around a building that was predominantly naturally ventilated, even though it came later than the advent of air conditioning. And so what happened when air conditioning was invented, this was in about 1912, Willis Carrier invented a sort of an affordable vapor compression machine that would do, with simple electrical input, would produce cooling on one side and heat on the other. And that liberated architecture from the tyranny, if you like, of needing to be responsible for climate. And the movement then developed that was around the international style, which kind of turned its back on environment and said it doesn't really matter what we build, we can make the buildings sort of comfortable by the application of systems. In fact, Crown Hall was never really comfortable until we went in actually a few years ago and did a major renovation, and by various subtle changes we were able to make it massively more effective. But I haven't got time to talk about how we did that today. But it's interesting that this was the sort of an early idea about a movement in architecture that was all about lightness, transparency, and an independence from the environment, and it was all about the systems doing the work. And that became the predominant architectural language of the middle of the 20th century. Architecture that was the international style. You can build it and put it anywhere, or you can design it and put it anywhere, regardless of the climate. And that's not the way that we think about climatic architecture. Brutalist architecture, similar thing. There's nothing much environmental going on here. One of the few really jaw-dropping buildings on the planet is the Beinecke Library at Yale. But it's kind of the worst best building in the world, because it is an absolute energy hog with its terribly thin walls and its incredibly close controlled air conditioning on the inside. But a thing of great beauty nonetheless, but nothing to do with the environment. It's all to do with creating an environment for books artificially. And I had the great good fortune to renovate both of these buildings and really understand how they were just terrible performers in terms of energy and environment. In terms of passive design, the glazing was all wrong, the windows were terrible, the building's overheated. I used to have my office here, and I'm sure Ed has had an office here as well at some point in this east-facing facade, and you literally needed to be in your shorts even in November at 7 in the morning, because the solar gain was so extraordinary. So there was nothing about environment in these buildings, and nothing. And now you get to a new world of the new international style, or neo-futurism, whatever you want to call it. But actually, it's kind of using technology as a little bit of an excuse to. It's still got big air conditioning systems, and it's still got a kind of absolute focus on transparency as a way of producing architecture. So that's something we've sort of pushed back on. I am going to show you some big glass houses a bit later. So just to go back then to our early part of our time as Atelier 10, where we began and where we started to sort of do explorations in low carbon design was on a project called the Earth Centre, which was in Yorkshire in England. It was set up as our National Centre for Sustainability. And it was one of the first projects we won as a young practice. It was quite extraordinary. It's a building by Jan Kaplicki and Future Systems here, and a building by a firm called Field and Clegg Bradley here and here, which was an exhibition centre. So the site was an old colliery spoil heap. And it was basically remediating land that had been a big pile of coal mining tailings. So we stabilized the ground, built some beautiful gardens, but the buildings had to sit. I should also say there's two rivers here, and then there's also a fault line that runs right across the site, a seismic fault line. So we couldn't put piles down. We were trying to build about a 50,000 square foot museum space and gallery space here. So we couldn't put piles down. The structural engineers, the Atelier 1, were looking at building a rafts to support these big buildings. The thing on the front here is the first very large solar canopy we did. This was 20 years ago, a PV canopy sitting on timber forest thinnings for minimum environmental impact. But that's an aside of the main story. So I sort of said, well, you're going to have this big slab that's going to sit across the bad ground of the spoil heap. Could we hollow it out and push air through it and turn it into a kind of labyrinthine passageway, so we can make take hot air during the daytime, push it past all this concrete that we've cooled down at night, and use that to get some free cooling the next day. So we developed that into an idea, and so this double floor, which is a structural floor that's basically spanning as a big raft, we hollowed out, and what happens is that in the daytime the hot air comes in through here, it passes through the passageways till it gets cooler, and then it comes up through into the gallery floor above. And at night time, we blow cool air through the labyrinth, and we don't put it in the gallery, we dump it to outside. So we're storing sort of coof in the ground to do that. And the inspiration for that did come from our friends, the termites, weirdly. So termites are these extraordinary creatures that live out well, they're all over the world, but mainly you see them in Africa. And these nests can be 15, 20 feet high, and they're made entirely by these small creatures that are only barely an inch long, that are completely blind, and they're working without the aid of an architecture degree to produce these extraordinary structures. So their main ambition is to keep the queen, who is the creature here, precisely 30 to 31 degrees centigrade right through the day, even when it gets to 40 degrees centigrade in the daytime and down to sort of 10 degrees centigrade at night. And they do that by blocking and unblocking these holes in the structure, which basically allow an updraft to draw air in. When they unblock them, if it gets too hot, they unblock them, and the air comes in down these passageways, runs up into this huge underground chamber, which is this picture here, which has these spiral fins that are like heat exchangers. And the air runs up through these into the center of a nest where the queen sits. And in doing this, it drops the temperature from, say, 40, 45 degrees down to exactly 30 to keep it exactly at 31 degrees in the center. When it starts to get too cold, they reblock the holes and they slow the airflow down so that they can actually do this kind of temperature modulation by doing this. Their control system is entirely pheromone based, and they have some signal goes out from a queen in the middle to say, I'm too hot, I'm too cold, and the termites jump into action. When it gets really hot, the termites have been seen grabbing a leaf stem, heading down to the water table, or a seed pod, going down to the water table, pick up a dollop of water and put it in this space to get some evaporative cooling effect as well. So this giant space, which is big enough for a film crew to be in, because David Attenborough shot a sequence in here for Life on Earth, these things are enormous structures, all based around environmental performance. But what's going on here is a mixture of radiative, evaporative, convective, and conductive heat transfer, all of which combine to make a kind of environmental system, all controlled by not by engineers like me, and it works. It works really well. The other inspiration was passive design. Was these buildings in a little village called Costozza in the Veneto, north of Italy. This is where Galileo Galilei used to go for his summer, because it was the coolest place outside of Florence to stay up in the Tuscan hills. Now, there's a beautiful illustration here by actually it wasn't by Barbara Kender, it was by someone else, commissioned by Barbara Kender for a book she wrote. And this illustration shows the villa that we're looking at here with Prometheus, who's the god of sun, casting his waves, energy down onto the front of the building, while Zephyrus, who's the god of the southwest wind, I think it is, blowing the air into this cave system. And the air comes out in the houses through these marble grills. And in going through the caves, it cools down and basically provides air conditioning into the houses. And the architect of this sort of these wonderful villas had noticed that the caves where they kept the wine underground were all much cooler than the houses. And he thought, well, maybe and there's a whole cavern in the hillside that was cooler. So he basically joined all the dots together and made these fabulous villas that are all the first sort of first air-conditioned buildings in 18th century Italy. So there's another inspiration for this kind of thermal mass storage. It's not complicated, really, let's face it, but it's really nice, and it's a very elegant solution. So we took some of these ideas once we did the Earth Centre, and that all worked well. And we were doing a competition for this project, which is Federation Square in Melbourne, a massive government or state-sponsored arts centre, which included a very long atrium building. I hope you can see my mouse running up and down. There's a long atrium building here that was highly glazed and was open at both ends, but that we wanted to keep comfortable inside on a hot Melbourne day. Here, there's a sloping piazza which had no program underneath it, and the whole thing sits on top of a flat train crash deck with the railway lines running in under here into the railway station. So again, there was a void space here, and I said, well, is there any way we can pull air in from the cool riverside through underneath these voids, through some labyrinthine passageways, and push it into the building? And the client sort of said, well, yeah, why not? So it wasn't quite that simple, but we went ahead, and this is the cutaway, taking the slab off the top of that before we put the slab on, really, for the big square. There's the station in the background. We built these sort of labyrinthine passageways of concrete walls that are rippled to maximize the surface area. And they basically sit in line between sort of an air intake. The air goes through the labyrinth, through some air handling units, and then feeds out into the atrium space to keep it comfortable. And we basically have some clever things going on. So in the daytime, we do a bit of rainwater spraying like the termites do to bring the temperature down a little bit more. And then we push the air into these passageways. The air runs through about 300 to 500 feet of tunnels before it comes out to a little air handling plant here, and a fan blows it into the space. And this is the space here with the grills in the floor where the air comes out through. So And then at night time, we kind of reverse the whole thing and move some dampers around. And what we do then is bring cool night air in, because it's nearly always cool in Melbourne at night, and blow it backwards through the passageways and back out and dump it out down towards the river, or push it out towards the river. And this was incredible, because it meant we completely eliminated any air conditioning in the buildings. So the buildings run completely on Labyrinth power. It's a real intergenerational win, because although you put a lot of money into building the concrete, and these days a lot more embodied carbon, although it was low carbon, low cement concrete, because it didn't need to be very strong. This will still be there in 100 years, in which time you would have replaced the plant 5 times probably. So not having to do that does save a lot of carbon. So then, and this is going to look a bit like a one-trick pony, we then won a competition for a headquarters building in Turkey, in Ankara. And this is just to show you that it can apply anywhere. So Ankara sits right in the middle of the Asian side of Turkey. So Istanbul's up here with the horn and so on down here. And so it's a place that has very high temperature variations. And this is typical diurnal temperature range. This is what you're looking for when you're doing a kind of thermal storage systems. You want ideally somewhere where the hottest part of the day and the coldest part of the day straddle the area you're trying to get to be comfortable. That uses thermal mass. So what that says is, if there's triangles here are sort of equivalent in size or less, you can in theory move the energy from day to night and get a sort of flat line of temperature that's in the comfort range. So of course, the standard air conditioning, the standard response to this problem of how to keep comfortable on a hot day in Ankara, is to put this in. And this is what you see in so many of the buildings. Just every building's got a split system air conditioner. And of course, these are sized to deal with the peak on the very worst day plus a bit. So they're working incredibly inefficiently all of the rest of the time, and actually are completely unnecessary if you design the building right. So we showed this to the clients, and the client was a Turkish Contractors Association. So these are guys who build buildings. And we said, well, if you put your building on a kind of thermal store, and if you maybe use all of your concrete slabs as thermal storage by putting some pipes in them, we think we can take all the energy from the nighttime, the cooling energy, and remove the need for air conditioning. So they thought this was great, because they're not the Turkish M&E Contractors Association, they're the Turkish Contractors Association. So they wanted to show the M&E engineers they didn't need them so much. And so we took it a stage further by even embedding pipes in the slabs, so that we run the air through the slabs. We do have a small chill beam, which very rarely gets used, just to chill the air down if we need to take the edge off if a room is very highly occupied. So this shows under construction. They basically decided to rather than do precast, they put tubing in the concrete that connects onto the ventilation system. And this tubing basically radiates cool or absorbs heat from the slabs at night, and gives us this ability to night cool the structures. So you've got overhead, you've got all these cool concrete overhead. That really means the chill beams don't have to do very much at all. They were so excited about it in the end that they decided to leave a chunk of floor out and light it so you can see the rebar and the steel pipes, and the whole building's become a showcase for kind of low carbon building design. So the Labyrinth works in a similar kind of way to the one in Melbourne, fresh air coming at night, lots of passageways underground. Here we used a kind of very, very low tech, dense concrete garden block wall with a rippled edge, just to get this roughness to maximize the thermal capacity. This was me approving the concrete panels for construction before this poor bloke was sent down into the basement for a few weeks to build miles and miles of walls with heavy block. But the end result is we originally started out with it being only about 4 feet high, but they decided they really wanted to take guided tours through it. So the last time I was there, I took 120 architects through it from the Turkish contractor, the Ankara Architects Association, and we managed not to lose any. Biscuit crumbs trailed through with the answer to make sure they could all find their way back out again. But all these, it really was a game changer. And in the end, instead of all those air conditioning units, we have one heat rejection unit for the computer room, but the rest of the building runs on solar power and energy storage. And it kind of goes back to, it was the first LEED Platinum building in Ankara. And it went back to, someone said this to me, so I feel I can use it. Said it, take another Bucky quote, just to say, you never change things by fighting the existing reality. To change something, build a new model that makes the existing model obsolete. And that's kind of what we tried to do on that project. And it really did, I hope, ultimately will move the dial in Ankara and make people realize they don't need to plaster buildings with air conditioning units inefficiently to make them work. So that was a good triumph. We've also did work, Ed mentioned the Croon Hall at the Yale School of Forestry, which was one of the projects we built at Yale with Michael Hopkins and his team. A really advanced environmental building. And I could tell a whole story about this, but I'm going to go on and talk about another one that we've done. So I just draw your attention to the kind of appropriate fenestration for the daylight requirements, shading on east and west facades, PV panels on the roofs, and also a deep well ground source energy system running ground source heat pumps for a bit of heating and cooling, and then indirect evaporative cooling like the termites again to do any air, to cool the preliminary cooling of air and all the air coming from the floor. So lots of things integrated into the architecture that did a job. And with the same architects, with Hopkins, we did a headquarters building for the World Wildlife Fund, not the World Wrestling Federation, called the Living Planet Center. So this is an air rights building. It's built over a public car park, which we closed for a year or so while we did the work. And it's a really, one of the greenest buildings in England. It's kind of a benchmark for sort of sustainable development. But at the same time, it combines, and I think Ed referred to this, it combines beauty in architecture with performance. And it does that by a really careful application of daylight as an important design driver in a sustainable building. It thinks about biophilia and the role of nature in the building. And then technically, we just think a lot about things like thermal mass and energy storage. So actually, these timber roof panels are all filled with a phase-changed thermal mass material. And the concrete down here is also designed as part of our energy storage system for night cooling. The building is what we call a mixed mode building. So it operates as a naturally ventilated building for half the year. And then for the coldest days in winter and the hottest days in summer, the windows are closed. And we draw air in through some tubes in the ground called earth ducts that supply through a fan unit into an underfloor air supply system, so that we can condition the space again using earth energy and really linking the building into the ground. The residual heating and cooling comes from some closed loop energy piles. And the people who live in the building, work in the building, get signals on their computer. This is something we developed at Croon Hall every day to say either today is a natural vent day or today is a mechanical vent day. If it's a mechanical day, the red light comes on and you don't open the windows. If it's a natural vent day, they get a green light on here. The vents here open, which link to the rooftop cowls, and they get a nice breeze through the building, and the building runs without any systems at all for the rest of the time. So it's kind of super, it feeds back to the staff and the occupants, so they feel part of the kind of operating system for the building. And then these earth tubes linked through to these structures outside come along about 80 meters in the ground before they feed up into the air handling units and into the floor. And then the ground source energy does the rest. We've also got rainwater harvesting and lots of other good things going on there. So this is kind of architecture and engineering, how I wanted it to be when I started. It says, we can do better, we can make great things, and it doesn't have to cost the earth. So here's these earth tubes going into the ground. Again, they're very termite inspired. And these are like the earth tubes the termites put in to pre-cool the air coming in. But what's interesting is this measurement of what's happening. So here you've got, we don't get really hot days in the UK, but here we had 2 33-degree days, which is probably about high 90s in your currency. And the air coming out of the earth ducts is this blue line, and it's coming out around 17 degrees centigrade, which is 60 something. And that means that you can use that for free cooling, even on the hottest of days. You don't need to do any mechanical cooling. We're just using the energy from the ground. And then by blowing air through them at night, we can recharge them to make them cool again. So the next day, they can also do some more cooling, even on after a few hot nights. So this is kind of when we call it a thermal mass system. This is doing everything that we want it to do. The other thermal mass system on the project is these earth energy piles. So we've got about 42 100-meter, 300-foot deep closed loop piles. These are the pipes being pushed down into the piles, and we basically run a water glycol mix through them, and we run a heat pump so that we use the ground as our energy store. And because the ground is always at around about 12 degrees centigrade, we can be really efficient taking heat out and pushing any cooling back into it. So there's lots of earth contact in all that. On the roof, we have PV panels everywhere for solar energy harvesting. And then this was the first project where we found a whole new currency. We started to use carbon in construction, embodied carbon, as a new currency. People are getting incredibly interested in this. I'll come back to this a bit later. But this is the thing that we're doing at the moment more than almost anything else, is studying every material we put in a building and trying to understand what the carbon intensity is of the materials that we're selecting, and how by just choosing better or by driving decisions out of a supply chain, we can make more effective buildings. So on this project, we saved 4 million kilograms of carbon, or 4,000 tons of carbon, versus our sort of reference building, which is a sort of standard building, at no extra cost, just by making good decisions about materials. So all of these things are part of the architect's journey now, to understand the impacts, the environmental impacts, all of this. But even so, this is still a spectacularly great building, and one that everybody who goes there adores. It's just a lovely, lovely place to be in. So now I'm going to move to Singapore, and an extraordinary project that we did, after winning an environmental design competition in 2008 with Andrew Grant of Grant Associates and Jim Eyre of Wilkinson Eyre, working with Atelier 1 and Atelier 10, and Land Design Studio for exhibitions. It was an extraordinary brief to design a garden to sit on a 55-hectare site on some reclaimed land on the edge of Singapore. So for those of you who know Singapore, this is Marina Bay. The opera house that we did many years earlier is here. And this is the famous Moshe Safdie, or infamous Moshe Safdie hotel with the three towers and the surfboard on the roof, which you'll see in a minute in some photos. And the project was to design a botanical garden with 2 of the world's largest cooled conservatories. And the brief said it had to not use any more energy than a conventional office building in Singapore, which was a bit of a challenge. So this, I won't spoil the story by showing the picture of the finished job at the end, but it's easy to talk you through it this way. So here's the Marina Bay. These are the 2 cooled conservatories. So the one nearest me on the picture is the Cool Dry European Plants Conservatory in Singapore, hot and humid. And this is the Cool Moist, which is tropical montane plants from mountainous regions. The rest of the garden are showcase gardens from gardens from around the world. And then we invented these things called super trees, which you could see on my first slides. And these are all originally part of the energy management system for the domes and for our energy center, which is over here. So they hide a lot of the vertical stuff, like a Richard Rogers tube, I guess, that do a lot of the work. These are mainly there for shading, so that you can walk around the gardens in the shade by being in the shade of the super trees all the time. So that's the shtick of the garden, if you like, and it links back to the city over an existing lake, which looks a bit murky here, but we were just using the plants to clean it all up. The challenge that this set us as environmental designers was beyond belief, really. We needed to. We're on the equator. Singapore's right, just sort of 1 degree north of the equator. So it's hot. It's hot and sunny. It's hot and humid. It's tropics. But we had to make it light levels of 45,000 lux, which is 450,000 foot candles, for more hours than at Eden, which is a project where we'd done some testing in the UK and where tropical plants had survived in light levels. But we also then had 3 different air temperatures we had to work to. The daytime, we had to be at 25 degrees centigrade and 65% RH. Nighttime, to fool the plants into thinking the day-night cycle so they'll stay alive, we had to go down to 17 degrees at 65% humidity or more. And for a month, every 4 months, the temperatures dropped to 13 degrees centigrade overnight and 70% RH to fool the plants again to thinking that winter is coming. So that's to quote a famous TV show, and to keep the plants, to make them produce leaves and flowers. So there was a really complicated challenge. And, to put that in context, the graph on the right here shows the light level in the conservatories, 45,000 lux versus an office or a home light levels. It needed a lot of light. And this was all negotiated with the botanical gardens, because we were looking at different species of plant and working with Transsolar Engineering, who were doing some testing. And what we decided was that we wanted to be able to grow anything up to sort of Dahlia, Aster, Ranunculus light levels. We'd leave the hydrangeas to it, don't need much higher light levels. And we would set this target at 45,000 lux. And so we embarked then on a real complicated journey. Now, just bear in mind, the thing about being in Singapore is there's 2 things. One is that you get a lot of cloud. It's in the tropics. You get cloud and haze because of the rain that you get in the tropics. And we were looking to put things like olive trees, which grow normally on a hillside in Greece that get 18 straight hours of sunshine in the summer, or Italy. They don't have a lot of cloud, they're blue sky. And so the daylighting was absolutely critical. This graph shows the amount of cloud cover. Nearly 62% of days you get cloud cover at 2 p.m. in Singapore. It's not a great, it's really tough to hit those sort of light levels that you get for plants in Europe. So we did a huge amount of modeling. When we did the competition, we were working on the basis of a fin structure that would let light through in the glass in between the fins. And we thought the fins would help us with shading, as you can see from this, because we were more worried about overheating than I can tell you. We were looking to try and get as much light in as we could without overheating. So we had to discard the fin. This didn't work. There wasn't enough bright light. We then looked at a truss solution with Atelier 1, where we had these sort of steel trusses. These are spanning like 100 meters with glass in between. That didn't give us enough light either. So we eventually moved to a really beautiful grid shell. So it's quite a lightweight grid shell with small members. And then the grid shell is just propped by these flying steel structures that basically stop the grid shell from falling over. So there's a double kind of structure. It's a really, really beautiful structure. And these are some of Neil's drawings of the structure as we developed it. Not actually how they ended up, but it's just some nice hand sketches. But one of the bits just to notice is the initial hanging system for the grid shell to the glass produced all of this clutter, which made it really blocked a lot of light out. So we went through a process of, even to the point of mitering the steelwork, so that we could absolutely minimize the shadow effect of the glass. So what you get is a very fine mesh of glass. I mean, it's still a lot of shading, a lot of structure, but compared to when you look at the size of the thing it's spanning, it's a phenomenally light structure. And then inside the glass houses, you can see here we've got baobab trees and pine trees. Just to note here, we also have cooling in the floors, and we push air out through these walls. But I'll come back to that in a minute. So having got all that light in, we've got an issue. We've got a lot of heat coming in with it. So how are we going to deal with that? So we did do a lot of work on the glazing specifications. I mean, we basically used a really high performance selective glass that gave us around 65% visible light transmission. But using coatings, we only get about 35% G value, which is the solar heat gain from it. So by picking the right glass, we were able to get light without heat, with less heat. But even 0.35 at 1,000 watts a square meter of solar energy gives you 350 watts a square meter, which is a lot of energy coming in through it. So we also then, working with the architects of Wilkinson Eyre, came up with a system for shading the structure on the outside, so that at certain times of peak times of day, we're able to deploy the shades when it's very sunny. And we don't always have them all the way out. We can have them partially out to reduce the solar gain, but at the same time, not interfere too much with the daylight that's coming in from the north side and in the gaps in between. So this was a test run for the shades, but this is how we were able to do to get some additional shading to reduce the cooling loads down to a manageable level. So this is them as you're inside, as they deploy, and it's actually almost like a bit of theatre as they come out. They're basically just a sailcloth, and the technology is just cable driven, so the cable rolls back into the main structural arm, and I haven't got a picture of that, but it completely disappears when there's no need for it, and all you see is wires, which are a long way away. So we did. Having finished all the lighting design, we then had to figure out how to keep the thing cool. And we knew we only had people in certain places. So our idea was just to cool the places where the people were. So we developed, using computational fluid dynamics, we developed a system for just bringing air in at low level, provide cooling here. And then we have cooling pipes in the floor, which drag, when the sun hits the floor, instead of it heating it up and radiating, it just takes the heat away before it can re-radiate. So it reduces the solar gain. The plants themselves absorb about 70% of the energy that hits them and turns it into photosynthetic energy. So they don't re-radiate heat beyond about sort of 11 to 15% on different species. So the more heavily planted the building gets, the better it is in terms of absorbing energy, which is quite a useful thing. But we do still have quite a bit of kit. We've got an air handling unit plant room back here that pushes air out into these wall systems that basically release the cool air into the space, and then we have the cooling pipes. So I'm going to come back to how we made that zero carbon in a minute. So this was all about just conditioning the right areas. We allow the thing to stratify, and we release the hot air at the top to make it comfortable. So this was the beautiful plant room before we filled it with kit. This sits at the back of the gardens, which are in here. And then, as I say, we put miles and miles of tubing in the floors, and these are the air grills to let the air come in very slowly and at sort of not at very low temperature, just to keep the place comfortable all the year round. And this is some construction shots of the vents going into the flower beds. So these are 4-meter deep tree pits that have the earth is sort of mounded up in here. You can just see Safdie's hotel in the background. It was finished by now. And then these extraordinary pictures of this is the air supply ducts built into the walls. And the only air duct you see in the whole building really is this tube that goes up as our return air, which sucks the air up from about 20 meters up and takes it back to the air handling units over there. So it's a kind of there is kit in there. It's not nothing, and we have sensors all around the building that sense this is the radiant temperature, the light level, and then we have a sniffer in here that measures temperature and humidity. And the displacement terminals that were cantilevering out of the flower bed, you can now see sort of buried in amongst the trees here. And the trees have been absolutely brilliant. They've done really well. So that's the European dome. The other dome is Tropical Montane. So this is full of mountain plants, and it's much more humid. So, and the story here basically is, as you walk in, you feel this incredible humidity. There's a big waterfall, and then you go into an elevator up to the top here, and you spiral your way down Neil Thomas's unbelievable suspended ramps that are already featuring in movies. You might have seen them in, I think, Mission Impossible, or one of those films had a thing. Certainly the Crazy Rich Asians a lot of it was filmed here. There's a wedding ceremony filmed here, which was kind of wild. But every half hour we fog the whole place with foggers to take it up to 100% humidity, and the plants love it. And it's they really have been thriving in there, and the light levels are great, and everything is surviving. The more than surviving is doing really well. It's been open about 7 years. But our challenge as engineers, and I don't know if you'll be familiar with this table, it's called a psychrometric chart. This looks at temperature and humidity up here. And our target design conditions are in these dots to the daytime, the cloud forest and the flower dome, and the day and the nighttime, what we have to do to make the plants like it. All these green dots represent the weather in Singapore. So it's basically always hot, always muggy. You never get a cool night except for one stray green dot here, which I don't believe. So we basically have to dehumidify the air and then cool it. So that's what the systems had to do. And we had to come up with a way of doing that in a low carbon way. Now, in the course of the competition, we decided we were going to use a system called desiccant cooling. So that uses basically, like, when you buy leather goods or electronic goods, you get a little bag in there that says silica, do not eat. Well, that's a desiccant. So it absorbs moisture and stops it from, just absorbs moisture. And you can push the moisture out of it again by putting it in an oven or in a microwave to drive the moisture off. So a desiccant is you can regenerate, but it will absorb water. So what we did was to come up with an idea for using waste energy to drive the whole garden. Now, Singapore, our client in Singapore, has a program of managing the sort of 2 million plus trees that they've planted since the 1960s. And wherever you go in Singapore, you see these trucks that are doing tree maintenance, because there are trees everywhere. And it's what makes Singapore much cooler than other cities in Asia. Because, as I said, the trees absorb all that energy, solar energy. So we asked the client, where did all the trees go to get cut down? And he said he didn't know, but he'd find out. And he found that it was being sent up the road and mixed with packing case waste and incinerated in a plant outside the city. And we said, well, can we use that energy as a source for our garden? So what we do is every night about 15 huge trucks come in full of wood waste from the day's prunings. They go into a 500 cubic meter store, and then they go into one of the world's biggest biomass boilers. It's about 7.5 megawatts. That generates steam that drives a turbine that makes power that drives the cooling. Then the waste heat that comes off that process goes into our desiccant drying process. And so we use the desiccants to dry the air, and then we regenerate the desiccants using waste heat from the timber. And then all the waste that comes off there, the ash and stuff, is used as a high-grade fertilizer and also in cement replacement in Singapore generally. So we take a lot of ash out of the boiler, and that goes off to a cement replacement program. We also, the super trees have PV panels on them, and they also feed power into the lighting systems. The waste heat is pushed out through the super trees in up the central cores of the super trees. So there's like a whole, it's a very technical solution, but what's interesting about it, I suppose, is about city. Ed mentioned about city dynamics and how do you start to think about circular economy processes at a city scale. So this took basically a waste stream that was being incinerated and turned that incineration process, which is about all you can do with it, turn the incineration process into a virtuous process. We do scrub the flue gases, so we absolutely minimize the emissions. And in fact, this is the boiler, and there's the wood chip going to its certain death inside the boiler. And then if you look closely at this big super tree here, which is right by the entrance, you can see a carbon steel flue. So it's a 18-inch flue that rises up through the center of the super tree, and that's where the flue gases discharge. And then all you can see for the systems is a small set of cooling towers that dump some waste heat off the chillers after it's been through the three-stage cooling process to the turbines. So we've got ourselves a kind of complete environmental system that actually is, in the end, it drives some pretty big kit. So we have very large chillers that do actually generate the chill water to keep the rooms cool. But overall, we produce more energy than we consume on the site, and we're actually exporting energy to other parts of the garden to make the building net zero. So we overachieved in a way on the original brief, which was to make a net zero building. Now, there's lots of reasons you might say, well, why would you build a glass building there? And it's there because people in Singapore don't have much space. They live in very tight accommodations, and this garden was kind of a gift. One of the many parks around Singapore is a gift to the citizens who can walk freely around the 55-hectare garden, and it's packed. It's wonderful. And then that you have to the pay point is only inside the biomes themselves. So in many ways, it's a great story, but it's also with it came through our friends at Land Design Studio, a fantastic learning experience. So the whole basement underneath the mountain is a big gallery space you walk through, and you learn all about on this interactive thing about how the energy is produced, about how the horticultural waste is used, how it's, and it tells the story back to the city and hopefully inspires others to do well. But it is also a bloody amazing place to go. At nighttime, it comes alive. They have light shows on the super trees and stuff, all powered by renewable energy, of course. It's a truly, if you are in Asia, it's definitely worth a visit. On the back of that, we were asked to work with Moshe Safdie and Changi Airport to build a new project that's called Jewel that opened just recently. And this is taking it to another level. So this is another garden in Singapore, working mainly off renewable energy being generated in the airport, but where we have looked to grow this enormous forest garden. This is working with PWP architects, landscape architects rather, and it sits actually in the middle of the airport, on top of a car park and the 5-story shopping centre that then has this extraordinary thing in the middle with the world's biggest indoor waterfall. Here again, we had to do massive amounts of work to resolve the competing demands between people and plants and heat and comfort. So we've developed new tools, which is I'm starting to get into what we're doing now, which is the tools that we have using Rhino, Grasshopper scripting, using Ladybug, all kinds of other things. We're able to ray trace from every point in the garden through the roof, looking at obstructions from the roof and up to the sky to try and really understand where we've got good light, where we've got bad light, where we've got too much light, where we need to change the glass panels to add fritting to reduce the demand. And so many of these panels have got different levels of frit to suit what's going on underneath, tracking to the sun path. So again, spectrally selective. And then where we needed more shade, we've sort of developed these clever little shades that help to provide comfort in particular areas to take you out of the radiant comfort zone, the radiant temperature zone. So these projects sort of get slightly madder and madder. This one's actually got a railway line going through the middle of it that we had to analyze as well. But one of the hardest things to do on this one was to understand, I talked about the fact we have air at floor level, and that's what we try and do, just only condition that places where people are going to be. So we had to condition sort of just the bowl, not the whole thing, and that was the goal. But we very quickly realized in doing some CFD modeling that what was happening was all the hot air from the top was being entrained by the water as it came down and was smashing down into here and basically messing up our entire cooling system. So we did some CFD analysis, and we went back to the architects and said, we need to put a glass screen here and here. I think you might see it in the photos. So this glass screen that runs around here is all about trying to deflect the airflow back up before it spreads out and destroys our cooling in these spaces down here. And to do that, we used a lot of CFD modeling, which shows what happens against the glass screen and how it does help us to not flood this area. What would happen otherwise, all this air would flood out this way and would just make everyone wet and humid and too hot. So again, this was actually going to the point where we were modeling individual droplets to estimate the drag, and then putting thousands of them together to understand what was happening with the evaporation and the humidity in the space. This thing is pretty bonkers, and it's supposed to only run about 10 minutes an hour, but it's so popular it runs pretty much the whole time. And these huge trees in there that are doing very well. And then a massive job on integrating all the air supplies. So wherever people are, there's a little pool of cool air. And again, there's the pipes in the floor to keep them comfortable. But the rest of it is a much warmer space as appropriate to the tropics. We have the embedded chill water pipes in the floor as well. So this is at Changi Airport. I don't know how I'm doing for time. Am I okay, Ed, or should I be wrapping up? I've got a couple more slides just to talk about the current context.
Yeah, take a few more.
Yeah, sure. Thanks. So the latest, what we're looking at now in the UK particularly is what we were calling sort of the dash to zero carbon. Everyone's claiming to be zero carbon, zero everything. And in fact, in the book that I wrote from our 25th birthday 5 years ago, Paul Finch, who's a quite well-known editor of the Architecture Review and the Architect's Journal, wrote about our work and said if only carbon still stank, things would be so much easier for designers like us, which is kind of true. But what we're looking at in construction a lot these days is two different sorts of carbon emissions. One is the embodied carbon, which is the carbon in the materials that we use to build it. And that's carbon that you're going to emit immediately when you build. So you get a big pulse of carbon into our system, into the planetary system when you build something. And this is only really starting to dawn on people and become a design driver. Over the years, you might have some fit outs and refits and things. This is thinking about an office. And then in 25 years, you might do a major refit and then you carry on. The operational carbon, the CO2 emissions happen from the year you occupy it, and then they gradually build up over time, and it's a total amount of operational carbon. And of course, if you build a very efficient building, your CO2 emissions go down, and so the operational carbon becomes almost less of an issue than the embodied carbon. So over time, what we're seeing, is in a normal building, the operational will overtake the embodied in time. But as you get better and better at doing high performance buildings, the operational carbon is becoming much less of an issue, and the day one carbon, which is the issue we've got right now, minimizing carbon emissions, is the big deal. We kind of have a good understanding how to do operational carbon to get towards net zero, which is a mixture of passive design I've talked about, active efficient systems, efficient equipment and plant, application of renewable energy gets you somewhere close, and the decisions you make in a project, depending upon regulations, will be somewhere in this range. And you then use potentially, all electric building, you use green energy, or perhaps you buy offsets if you want to get to something that's sort of net zero. And then beyond that, you might look at sequestering and things to get to carbon positive. But it's very, very difficult to get to a building to be operationally carbon zero without some sort of green energy use. And part of the issue we've got right now in the UK is that it's really complicated to figure out how our all-electric future is going to work. And the reason for that is that the grid electricities in the UK has reduced the carbon intensity of the grid electricity, has transformed with the application of particularly sea-based wind turbines and solar energy, to the point where it's now, in about 2018, there was a crossover, where previously natural gas was our best fuel for buildings. Now it's no doubt electricity and heat pumps are the best way to go, because they have much, much lower, with more efficient grid power, they have much, much better efficiency. But the double challenge is that this is an app I have on my phone. I don't know where it is, but you basically, it's called Grid Carbon UK. You've got one for the US as well, and you can see instantaneously what the emissions of the grid of our national grid are. So I am just going to risk trying to show you now. So right now in the UK, we are, it's a windy night, so we've got 35% of our energy. I don't know if you can see that. 35% of our energy is being produced, and we're down at 135 grams of carbon per kilowatt hour. And what happens is, as the power demand goes up, or as the wind drops, we have to bring in more coal power and more other import more power, perhaps some biomass, and that drives the carbon up, and the country goes a bit browner. And a typical day, it's around that. So using carbon as your calculation thing is a bit tricky because it's constantly changing, but it does mean using energy storage is quite a big deal. If it's complicated in England, it's horrendous in America, because you've got such a diverse power generation system, and you've got some sort of cleaner energy over here in California and down towards Mexico, and then up here it's getting pretty dirty in Cincinnati. I wish I could see where you were. It's not so great, and New York's pretty dirty because there's a lot of coal. So this is more of a vexed question in the States, and we're struggling to understand how we leverage kind of emissions and performance in our offices in America to figure out what the best system is. And it's not by any means as uniform as it is in the UK, because we have a single national grid. In the US, it's quite challenging. You have to know what your power grid in the area is to understand what the best solution is. So it's not always the same. So from our perspective, what's happening is the RIBA and there's a London group called LETI, which is the London Energy Efficiency Transformation Initiative, which is a non-governmental thing. It's starting to look at setting targets in both embodied and operational carbon, and saying, right, today we're at about 1,100 kilograms of carbon per square meter. We need to get to 500 by 2030. And most of our clients are setting that as a hard target that we have to get to. And that's trying to drive change in both design and in decision making, and particularly in supply chain, so that our supply chain gets more efficient. And then operational carbon, similarly, even tougher, because they're looking to reduce it by sort of 75%, which is a big challenge. So we've got various targets that are coming in. And what we're finding on buildings is that we're looking really hard at looking at concrete, particularly trying to find alternatives for concrete, which is responsible for 8% of global emissions. Finding ways of avoiding using concrete in the building, or using products like SEM-free as an ultra-low alternative, and using a lot of GGBS replacement things. But the other things we're finding, which is kind of interesting, is when you do something like this on a building, which is to sort of step back and put a big overhang and put big offset loads on a column, you can add something like 20% to the embodied carbon of the structure, if not more. If you change the grid of your building from being, say, a 27-foot grid on an office building to, say, a 40-foot grid, you will add 20 or 30% to the carbon emissions. So decisions that you make day one around grids and so on and particularly offsets, cantilevers, and all those sorts of things have a really big impact on embodied carbon that we're only really starting to recognize now. And I'm talking about now in the last 12 months. It's clients are interested in it. We used to know about it, but they weren't interested. Now it's becoming part of design vocabulary. So to the point where, this was a presentation I did last week on embodied carbon to give a client, sorry, it looks like it's shifted in a funny way, but it was giving a client an update on, in August 2020, we were at 704, our target is 600, now we're at 558, and the world is at peace. I can stop answering the phone, but we did that by using GGBS admixtures, high star steel, hydro-based aluminum, and so on and so on. So there's a whole new design vocabulary emerging beyond LEED and BREEAM and all those things. This is the equivalent on the operational energy. And here we're struggling because tenant loads are still pretty high, and we have our basic standards for tenants are not very intensive. So this is kind of a typical reporting thing that we're doing with clients now, which is completely different to the way that we were working 30 years ago. And I think that the process is all the better for it. But it's definitely, we're definitely seeing a massive change in the way that our industry is responding to this challenge of carbon. And I feel like after 30 years of shouting about it, it's quite great to find that we find ourselves in the center of the conversation in virtually every room we're in. So I hope that you as aspiring architects and designers can take from this a kind of thought that every decision that you make has a carbon impact. And if carbon needs to start to become our currency, if we're going to have any chance of really making a change to the way we live on the planet. And on that note, I shall draw to an end. It's very weird not having any feedback at all during the talk. So I can't see even a smiling face or anything, but I hope you've found that useful. You may all be fast asleep for I know, like most of my students at Yale. But anyway, I will stop sharing my screen. I'm used to nobody responding to me, so it never bothers me. Whereas you, I think, have quite an audience for the work you and the
the rest of the group at Atelier 10 do. I'm going to see if I can try to manage this. If you have a question and you're on the Vimeo feed, and Patrick, just be aware there is I think you're still lecturing on the Vimeo feed. You just ended. So there's a little bit of a drag. Just type it in and I will try to read off a few of the questions and police this for about the next 10 or 15 minutes, if that's okay with you.
Yeah, it's fine. Can you still hear me?
Yes.
Good.
So there's one question here. I was asking about earth ducts, and I was going to say to you, you'll have to come to Cincinnati someday because all the breweries used to be tucked into the hillsides of our 7 hills because all the cooling operated there, and they still stand there today. So there's a source of energy cooling for the whole city.
Brilliant.
But somebody asked about earth ducts, and they wanted to know, is there a building size threshold where it makes sense to consider using them?
Yeah, I think definitely. We find that when you go over kind of 3 or 4 floors, 3 or 4 levels, the amount of ducting you need to bring through and up the building becomes excessive. It's just pretty hard to manage. So I think the largest building we've done with them is probably a 3 or 4 story. You certainly on high rise, you don't really have the footprint, the ratio of ground, of sort of bigger ground to floor space to do it. So yeah, 2, 3, 4 stories. Single story, easy, but anything above that, it starts to get a little tricky. I have had some, genius ideas where we've done proposals for tall buildings where we put a labyrinth every 15 floors, where they used to put a mechanical floor, and you just but instead of using concrete, maybe use a phase change material so that we can just blow air through the building naturally at night to cool the thing down, and you shut that down and you use the coof you've captured the next day. And maybe one day before I retire, I'll do one of those. So it's not nothing's impossible. If it becomes enough of a selling imperative for clients to do the greenest buildings, which is what everyone's now trying to do, then these kind of ideas are starting to find some traction. It's not impossible, but it's different.
Let me ask you a question. The Singapore project is interesting because you get to the scale beyond the building, which I'm always intrigued by, and I know you probably worked speculatively on another scale. But given that some of the things you outlined at the beginning of the talk, that a lot of what's somewhat interesting is a lot of this is market driven. The market's now dictating that we all move in this direction.
Yeah.
Are you mostly working through private developers, or are you working with any governmental agencies to look at broader scope initiatives for city planning and provide new infrastructures for the 21st century?
I mean, I think in the US and in Asia, we're definitely looking at sort of, if not urban scale, at kind of semi-urban, at sort of city block scale or that sort of thing. We've been working with Columbia University on the Manhattanville campus. We've been working on various other university campuses where that's definitely the case. And we have a couple of projects where we're doing city scale projects. We've seen it a lot in China. Where you just never know what's going to happen. It's one of those weird things. You do a kind of $80,000 fee to produce a master plan with Foster's or something for a city in China, and then they take it away, and then you look at a magazine like 5 years later, and
there it is.
It's there it is. You think, oh, they did it, and you don't ever they never phone you back or ask you any questions. They just kind of build what you gave them. Which I suppose is a good thing up to a point. You never know if they built the right thing. So yes is the answer. I think you don't often get this nice. The Singapore story was a nice story because I was actually at a cocktail party talking to the head of the buildings, and we were really wrestling because the competition submission, we'd done the whole thing on solar power. Our sort of energy generation was solar, but we were getting really big panels, and then because it's cloudy for like 3 or 4 days at a time, so we had to do a lot of storage of desiccant. So these vast tanks of desiccant, which was really expensive. And we were starting to struggle to make it happen. And the guy asked me, how are you getting on with energy sources and things? And I said, oh, well, and I asked him, what does he do? And he said, he looks after all these trees. And I went, ding, the light went on in both of our heads at the same time. And we went, okay, we have the answer. And it was one of those wonderful moments that,
I love that. Yeah.
Wouldn't have happened if I hadn't gone to the cocktail party yet. That's the thing.
That's why I tell our students it's important to go to the cocktail party. I think we learned that in New Haven.
Yes.
Someone also asked, obviously you have, thousands of projects, I think at this point. They asked if to get examples of sustainable buildings that worked in predominantly colder climates.
Well, if you count of Northern Europe as cold, I'd certainly say it's the sort of examples to look at. There's a lot of work with GMW. In Berlin, in Holland, the Edge Technologies buildings in Holland are particularly interesting. We're doing the Edge Technologies project in London right now, but they have a building in Amsterdam that's kind of one of the most environmentally friendly buildings in Europe. We often look to Scandinavia for our kind of exemplar sustainable buildings. What you generally, because they just are good at it. They just have a way of adopting technologies in a very pragmatic way. Our developers have taken a lot more time to come to the party. And what they tend to do in Germany and in Holland and Scandinavia is they build much more defensively. All the windows have shades and shutters, and they design them to naturally ventilate for as much of the year as possible, and shallow plans for great daylighting and all those sorts of things. And it's things that we and you in America have kind of eschewed as a design language, and tend to go for the great big fat deep floor plates and big old windows that've got no shading on them. And then we just air condition the hell out of it and heat the thing. So look to the Scandinavians, look to the Germans. I wouldn't want to name any particular buildings, maybe beyond the Edge building, but there are lots. I mean, it's still in high rise. It's really hard to beat the Commerzbank. It's really irritating, because it's about 30 years old. But Foster's Commerzbank was an absolute sort of. It's not efficient. Okay, it's a headquarters building. It's not what a spec developer would build, but it's a fantastic environmental story built into that. It was so far ahead of its time. We still use it as a reference on projects when we're doing high rise all the time. We just built a Comcast tower in Philadelphia with Foster's, which is pretty good. This is the second one off. Bob Stern did the first one, and we've just done another one with Foster's. That's coldish in the winter, hotish in the summer, probably slightly overglazed by that kind, but we're very efficient. Lots of different types of systems that you wouldn't normally use in a US spec office.
There's a question from Unmesh, who's our thesis prize winner 2 years ago. He asked, and this actually is a topic of a number of our thesis students. They're looking at things like with cloud computing data centers, which are enormous heat and water resource taxations on the environment. Have you had any thoughts about the potential of these for heat recovery and reutilization?
Yeah, we have. I mean, the problem with them is that you put a lot of high-grade energy and electricity to drive the servers. So you're punching a lot of heat into a lot of electricity into the building to turn all the disks and things and whatever it is that they do in those buildings that make all the heat. And the heat that comes off them is not that hot, because by definition, you're getting heat off the back of the units. It's at 26 or 27, 28 degrees. Now, that's enough to need a lot of cooling, but it's not enough to drive an energy system for anything else. You can't boil water with it. You can't. I mean, it's just it's what we call low-grade heat. So the problem with these things is I think it's much more about building the data centers in a place where you've got cooling naturally available, like in the Arctic Circle or something.
Right.
So you don't have to. You've still got to get power to them though to drive the equipment. So the problem is it's always the endless problem with heat recovery on these sorts of buildings. The energy in the heat is such low-grade heat, which means it's not very hot. If you're getting heat off it like you do off a New York power plant or a Boston power plant that's steam, you've got something. That's why they drain steam, because you're dropping the condensate into the sewers. But you've got a byproduct which has a temperature that you can use. With this thing, the temperature is just not hot enough. We have tried. It's really difficult because
I think maybe it was you and I had a conversation about that. I know in the part of New England where we both have shared good times together, they used to run the steam pipes off factories to heat the roads in the 19th century. Another student, this is actually, I feel like this is a setup question, so I'll lob you the softball. It says, with the emergent conversation revolving around embodied carbon, how do we walk that tightrope between great architecture and unnecessary added carbon? Is great architecture worth the negative environmental effects? Take it away.
Absolutely. But I'd say use it wisely. It's like anything else that you do. If you apply, I think if you're utterly didactic about this thing, you end up with really boring architecture. So, one of my issues I have with something like Passive House is that it gives you a kind of, it just prescribes things too tightly. It doesn't give you the wiggle room to make great buildings. So I'm absolutely passionate at saying that architecture is not just about being carbon efficient. Sustainability is about creating great places for people to live in and live. And if a building is good, it'll last longer than a building that's bad that gets pulled down because it's bad. So I absolutely believe that but what you need to do is to use, if you can find ways of creating, if you're going to say, I'm going to blow some carbon on this feature, just like you blow a financial budget, go for it, but be careful everywhere else. Try and give yourself a budget, a target, and set yourself realistic, and so set targets, and then try and get the most out of it, and squeeze the most out of it. Because yes, you'll make some decisions that are not perfect for carbon, but if you can back it up with having a clear sensibility about all the other decisions you make, then I don't think there's anything wrong with that. I think we can still make great architecture.
Well, I think that's one of the things that I learned from you I've learned that from you a long time ago. There's things, including the projects you showed tonight, where you can't believe
real
carbon neutral or energy producing, but it's the capacity of you and your colleagues at the firm to think those things all the way through and work in early dialogue with the architects and the landscape designers to kind of really put all those cards on the table. That I think it's important for people to understand that you can be progressive about lifestyle choices. And I mean, it's interesting to think that such an extreme environment like an exotic plant house can be done in that way. But those are the places where, historically, real interesting innovations happen, from the British greenhouses in the 19th century right to what you're doing today. I'll get one more question. I know it's getting late and then we have to jump to a short event, but somebody asked, are the systems that rely on recharging by cooling overnight applicable to buildings that are occupied or in use 24 hours a day? If not, are there alternative solutions that work?
Yeah, that's a tricky one. I mean, if you can find a way of what we've generally done when that's happened is you say, okay, so at nighttime, I'm going to bypass the system, draw my air for the building without going through the system you're trying to recharge. And then you have another air inlet that you push through the recharge system. So it sometimes means you have to double up on louvers and things, and an extra night purge fan. But it's entirely possible to do it. You just have to run you couldn't do it in the Earth Center, but you could do it in in Federation Square, for example. So it's possible. You just have to think. You have to know that that's what you're going to do. It's definitely more challenge. What you can't do is overnight cool a building if you've got people in it, because they don't like it. They get cold. That's kind of the idea. And so when you're night cooling slabs and things in the space, you've got to be really careful you don't drop the temperature too much. But no, so it's a good question. It's you do have to think about that, and if that's what you're going to do, if that's the brief, then you have to add an extra layer of complexity to be able to do both at once. It's like doing that. I just did that wrong.
I know what I mean. Everybody should be aware Patrick is 5 hours ahead of us. It's almost 11 o'clock at night for him. So I know he works late into the evening because the work's so exciting. I mean, I think it just looks like you guys have enormous fun and really enjoy what you're doing.
Yeah.
And the projects are spectacular. And I'm really glad that you're able to spend some time with us so that the college and hopefully other people at the university who I think were on tonight got to experience a little bit of the level of work that you guys are doing, and very inspiring as always to all of us. So I want to thank you. Jay Chatterjee has come in on here saying that he was really inspired by it too. So I think you were a great choice for the speaker this year, and I hope everybody got a lot out of it. For those who have been listening, this is being recorded. I'll find where that gets stashed. It's on the video link probably. So I guess this is up there permanently, but we'll also keep it in our warehouse and storage of lectures that we keep at the college as well. So Patrick, I want to thank you. It's lovely to see you, and I hope someday you will take us up on the offer and come visit us. I know the students would love to hear you again sometime in a more informal setting where they can really benefit from your wisdom and your talents.
Thanks, Ed. I really do hope to be able to come over one day. I've never been to Ohio, and I must add it to my list and come see you guys. It's been a great pleasure, and thanks to Jay Chatterjee for sponsoring the lecture and for making it happen. So I appreciate it.
Okay,
And thanks to you.
very much. Good night, everybody.